Now let's move on to the most important part of this course, which is the working of stepper motor. The best feature of a stepper motor is that it can control the angular position of the rotor without a closed feedback loop. Stepper motor is simple, precise, and open-loop system. Let's first check out the working of the simplest one, a variable reluctance type of stepper motor. As you can see, this motor has 6 stator teeth and can be energized with 3 separate DC power sources. A stack of steel laminations constitutes the rotor. It has different numbers of teeth than a rotor, in this case 4. This is done intentionally so that only one pair of rotor teeth is aligned with the stator at a time. Now it is an easy explanation of the working of stepper motor. If you de-energize coil A and energize B, it is clear that the rotor will rotate as shown. It is clear from the geometry that one step size is 30 degrees. In order to get the next step, de-energize coil B and energize coil C. By doing so, coil A becomes energized again, resulting in the rotor moving to the position with the least reluctance. Here, the step size of this motor is 30 degrees, which can be further improved to 15 degrees using a small trick. When coil A is energized, the rotor is in this position. It's known already to us that when coil B is energized, it moves 30 degrees. Now think what happens when coils A and B are energized together. The rotor moves to a position between these two cases, or it will move 15 degrees. Now let's de-energize A after this, then energize C as well after reaching B. This type of operation is called half-stepping. So this was about the working of a variable reluctance motor. Moving on to the most commonly used and versatile stepping motor, that is the hybrid motor. Let us learn the functioning of a typical 1.8 degrees step size hybrid motor. A hybrid motor has an actually magnetized rotor with 2 steel caps. Thus, one end of the rotor becomes the North Pole, and the other end becomes a South Pole. This clever arrangement of the rotor and stator teeth account for the accuracy of this motor. Let's try to understand it. The rotor has 50 teeth. For better understanding of the stator teeth arrangement, let us assume that the stator has 50 teeth as well. However, the stator actually has 2 lesser teeth than the rotor, which means we have 48 teeth on the stator. Let's arrange the 48 teeth into 4 group pairs as shown. Now let's realign these groups. The green set moves so that it is half aligned with the rotor. The teeth of the yellow group are completely unaligned with the rotor teeth. The blue group is half aligned with the rotor. The red group remains in place. In short, the red set is completely aligned with the rotor. The other 2 sets are half aligned while the yellow set remains unaligned. Please note that the rotor end facing you is acting like the South Pole. The stator coils are connected. As shown, they are 2 independent coil sets. The stator forms a magnetized pattern when set A is energized as shown. One pair of stator poles acts as the North Pole and the other as the South Pole. These will be aligned as we know that as the opposite poles attract. The same polarity poles will be unaligned. When the coil B is energized, try to figure out what happens to the rotor. It needs to rotate by a small angle to align with the new North Pole. You can observe that this angle is 1/4 of the angular pitch. So, if we say that in other words, the rotor moves by 1.8 degrees, next set A is energized with the opposite polarity. Again, the rotor moves by 1.8 degrees. This process is repeated to achieve a highly accurate motion by the motor. The step angle resolution can be further improved by half-stepping. It is also worth notice that the north end cap teeth are placed in between the south end teeth. This way, the alignment of the opposite polarity poles is guaranteed again. That is how a hybrid stepper motor works. These are best for applications where precise movements and simple controls are desired.